Hey, welcome back. If you go back far enough in my content, you will find 2 or 3 videos about me playing around with optical components to build a centering microscope. That never led to anything but um, realizing that I know very little about optics. That's a different topic. But I always wanted a centering microscope. So somebody offered me it's a new old stock, I suppose, Nikon centering microscope with the wrong shank. It's a 40 taper, but didn't match the decal standard that I have. But I'm a machinist, so let me guide you through the story of me modifying this microscope to fit my mill and what it can do. So let's have a start. I got 2 boxes here. One is Nikon and one is Moore Tools. And both of them contain a centering microscope. Centering microscope is a tool, an optical measuring instrument that goes into the spindle of a milling machine. This one has a 40 taper NTB shank, which doesn't fit my milling machine. The taper fits, but the end of the NT taper is different. This has a cylindrical OD and a imperial ID thread, I think. And my decal milling machine uses a 40 taper shank with a S20 by 2 buttress OD thread. So there is an adapter from going from an M16 ID thread to this, but not you can't go from this to this without modifications. But I plan to modify this to fit my decal milling machine, cut the shank, turn a new adapter piece with an S20 by 2 buttress thread, and make it fit. This is quite nice because it has internal lighting. As you can see, there is a cable coming out the end, and there are 4 LEDs around the lens illuminating your workpiece. It has, of course, a crosshair on the inside, and the crosshair can adjust it with those set screws out here to be in center with the spindle. So I digress. As I mentioned, it's a measuring tool that goes into a milling machine spindle. It has an eyepiece here. You look in here. There is a pentaprism in here, and it redirects your view to be in line with the spindle, so you can center your spindle optically to any feature on the workpiece. Came with a transformer from 120 volts to 3 volts, which is a little bit, that doesn't work for me because in Germany we have 240 volt line voltage, 240, 400. And it also came with an edge finder. This is still in the original sealing wax. I will show it close up later. This butts up against a corner of a workpiece, and there is a extremely fine line etched into the top of this piece that you can aim with the centering microscope to align the edge. Because otherwise, if the edge is a little bit chamfered or rounded or something else that has not a very crisp edge, it's hard to use a centering microscope on it. So that's the Nikon centering microscope. Came with the original documentation, all in Japanese. So that's a super neat instrument. And the other super neat instrument that I want to talk about is this thing here. This is a Moore centering microscope. I purchased this of my old employer. When they sold the Moore #3 chick grinder that I had, I bought a few things. Large rotary table, a bunch of setup hardware, and the centering microscope. I didn't know that somebody put the centering microscope in the box of the rotary table, and I bought the rotary table, not knowing that there is a centering microscope in there. I was quite happy about that. But of course, it has the flange to mount it against the U-axis of a jig grinder. I don't have a jig grinder, obviously, but this adapter plate is only held in place with 4 screws. I already removed 3. and this comes off. Then it's a extremely nice and compact device, very short, and I figured I will adapt this to the HSK32 shank that I use on the CNC and also with an adapter on the milling machine, because I have one part family that I do that would greatly benefit from having the option of a HSK32 sintering microscope. I have to modify the shank of this one, and I have to modify and make an adapter to mount this onto an HSK32. My primary use for this will be a horizontal spindle of the decal milling machine with the HSK32 adapter. I'm not sure if this adapter plate here is an original Moore item or if my old day job made this. I'm not clear about that, but it doesn't really matter. This also has a very nice crosshair side picture, crosshair inside. That's also adjustable up here for X and Y. Okay, let's start with this one. I tried to find out how the shank on these is mounted, and information about these Nikon centering microscopes is extremely scarce. I barely could find any English-speaking sources. I found some pictures of a Japanese auction site that had the shank removed, and for all matter of purpose, the shank looked like it was screwed in. I already tried in the past to loosen it, but whoever tightened this down used sheer willpower to torque it down or Loctite. So I will give it another shot. Otherwise, I will have to cut off the shank with the microscope attached and modify it that way. But I would prefer to not do that. So that's okay. Benchwise has these convenient pipe jaws in here, very roughly serrated, and I already tried to put this in here. The pipe jaws can grab the NTB end of the microscope shank without touching the 40 taper shank out here at all. So all I'm damaging is the end of the shank that I don't need at all. So here you can see how the jaws grab this end of the NTB shank. And, well, that's a very secure grip. That's normally used to hold small diameter pipe for threading. In my vast collection of spinner wrenches, I happened to find one that fits perfectly. Like, it's a perfect match. It has exactly the right diameter here around the body of the microscope. And, well, let's see if we can knock this loose. I would prefer to not knock it because optics, but we'll see. Okay, that was way less than I expected. There we go. There we go. I think that's already. Oh, that's still. Boop. Okay. So that's where the shank's screwed in, and this goes right into the optics path of the microscope. Already cleaned it with a lint-free rag. Now I'm taking a ball of crushed aluminum foil to seal up the hole just for storing. Using crushed tin foil because that doesn't lint. And it keeps just stuff that's floating in the air here in the shop out of the optics. That would be rather annoying to clean. I have to cut down the shank to a length of 71.5 millimeters, so it matches a regular tool holder that I use. Then I have to machine a adapter with a thread that fits in here. This is a 5/8 thread with 11 threads per inch. already determined that. Apparently there are two standards for NT tool holders. One has an M16 metric thread and the other one has the 5/8 11 thread on the inside. Because yay, standards. So cutting that off. And I need a change gear to cut 11 threads per inch threads, 110 tooth. I'm just going to 3D print that. It's printing right now, and I have done 3D printed change gears in the past, and works perfectly fine. No problem there for occasional use. Let's go to the surface grinder and abrasive cut this end off. Moreover, at the surface grinder, I have a magnetic V-block in a grinding vise. I figured I can just drop the shank in here, and with the V-block tilted, and this presents me with the cylindrical end of the shank horizontal. I just eyeballed it, then I took an indicator, got it in contact, found the high spot by traversing the table back and forth, like here, locked the table in place, just with the table stops, zeroed out the indicator, then I traversed over the cylindrical portion here and bumped the V-block around until I got a 0, 0 reading end to end on this. Super easy, very non-dramatic setup. Not really a precision setup here. And now I'm using a 1mm cutoff wheel to just lob off the end here. Here's the cutoff end. That worked quite well. And you can see that there is still about 4 threads remaining in the tool holder here. And I'm pretty confident that these 3 to 4 threads are plenty enough to hold a microscope in the spindle of the milling machine. It's not like I'm going to cut with the microscope. That would be unpleasant. I have to... This looks awfully out of center, by the way, but that's due to the fact that there was no chamfer on the thread, and where the thread exits the hole, it looks, of course, like the bore is offset to one side. If you look at this, it's center. This is very deceptive off-center, just by the way the thread leads out here. So let's see how we continue. Another funny grinding setup to face the end of the shank. I have 2 1, 2, 3 blocks down here. Well, parametric blocks, but for the sake of it, I'm just calling them 1, 2, 3 blocks. And I have the same magnetic V block as before. Behind it, tilted by the taper angle of the tool holder. In reality, I pushed it up against each other, making sure the face of the tool holder rests on the blocks, turned on the magnet, and then tightened the vise, so everything self-aligned and pulled itself into contact. Very simple. That gives me a safe setup to clean up the back end that we just abrasive cut off. So it's grinding is often just stacking things on top of each other until you have your desired problem solution. And that was all that's needed to clean up the abrasive saw cut. I'm going to put this on the milling machine. I'm going to cut a shallow recess in the back here to center up my thread adapter that I need. Otherwise, the hardened 5/8 11 thread in here will not be able to properly center the threaded adapter in there. I want a little bit of a cylindrical recess in there. So I could grab it on the lathe in the 6th jaw, and it probably would hold up to do some hard turning or hard boring out here, but that's an awful lot of overhang. Instead, I'm going to put it on the milling machine on a faceplate and grab it with 2 strap clamps from up here, or over at the milling machine, and this is a funny setup. This is the indexing head with faceplate, and I bolted a fixture plate to it with a threaded hole pattern. I made this years and years ago, and the tool holder is up on two blocks, so it clears down here. Now I want to strap clamp it down, but I need the upper end here to indicate it's true. So I need to hold it somehow down here. And the shank has this relief in the center, and I figured I'd just take a ring of an old ball bearing, drop it over here, and do this. Just clamp on this ring, and the ring will push or pull the tool holder down onto the blocks. This will be a little bit tricky to balance out the two clamps, but I think this could be a reasonable good and stiff setup. You machine a little bit of a recess back here and also chamfer it. This setup would work similarly on a lathe with a faceplate, but I don't have a faceplate for the Weiler lathe. So now it's clamped down a little bit. Now I can indicate this holder to run true to the spindle of the indexer. That's as easy as bringing in a dial test indicator, in contact, and then doing the usual bumping it through. Okay, we are off extremely far. That means that we have to move the clamps along a little bit until we are in a good position. Otherwise, we are going to put weird side stress on the studs. Oh, okay. The buttress thread that Deckel uses doesn't have a huge tendency to pull a tooling taper off center, but still you want to have it as good as possible. Now it's just a matter of tightening these 2 locking screws or clamping screws down evenly so that the tool holder doesn't move like mad. That's yeah, that's 20 micron. I think I will just live with it and call it good enough. Oh, I'm stupid. Instead of trying to bumping this contraption up here around that's already tightened down, I can bump the entire fixture plate on the faceplate around. Just by doing this. Hey. Well, that made my life just a whole lot easier. Yeah, that's good. I'm happy with this. 0 on the indicator. So that, yeah, that's fine. I can work with this. Man, that's a nice style test indicator holder, isn't it? Sure, you would love to have one of these yourself. And the good news is you can make one yourself because I released the drawings for this thing for free. Link down in the first comment. Okay, got a 0 here. Got a 0 here, mostly. 0 here. This is not super critical because we are machining a recess by rotating the table. So a rough center is good enough here. No need to single point indicate the true center of rotation. Let's see if a normal 6mm 3-flute carbide end mill is good enough to bite into this material. I have not hardness checked it, but as I have grabbed it before with the pipe jaws on my vise and it didn't leave a scratch, I'm not too optimistic about this thing being soft. So, touched off, I'm feeding down the entire 2mm of depth, and while I rotate the indexer, I will slowly move, well, I guess I will slowly move in the X direction and cut the counterbore to size, or the recess, depending on what you want to call it. Diameter will be 17mm, so it's not critical because I'm going to match the other part to it. Okay, that went way better than I expected. Let's change to a chamfer mill and chamfer both the thread and the edge of this little counterbore that I put in here. That doesn't look too bad. Put on a nice big chamfer on the outside, chamfered the counterbore and the thread. That looks very civilized, to be honest. I'm quite happy. So let's tear down the setup and make this threaded adapter and call it a day. This is one of the cases where it feels like doing it on a mill with a rotary setup, which tend to be a little bit more complicated and less convenient than on the lathe. But this feels... Uh-oh. This feels like this was one of the cases where a rotary setup was easier. Yeah, the ring that I used to hold the tool holder down press fitted itself in this clearance area. But as I said, there's a clearance area, so this doesn't hurt us at all. Could knock it off of a copper drift very easy. But yeah, I'm extremely happy how this came out. Looks really nice. I'm happy. So meanwhile, my electronic plastic grouping slave made me this 110 tooth change gear out of PLA, 0.2mm layer height, and I think it's printed with 3 perimeter walls and about 20% infill. Should hold up perfectly fine. I did this in the past. One day I will make them out of proper material, but for now these will do. So this will allow me to cut the 11 threads per inch thread. Deckel chose a 20mm OD 2mm pitch buttress thread with a 45-degree and a 5-degree angle. 45 on the non-load bearing side and 5-degree on the load bearing side. I have read very often on the internet that Deckel chose this thread style because it can take very much axial load in one direction, which you would need for a tool holder. I think that explanation is bogus because a similar sized 60-degree flank standard metric thread, you could tear the entire machine apart with that thread. No need to have a thread form that allows for a higher load bearing on one flank. That I don't buy that explanation at all. What I think is, I think Deckel was of the opinion that the buttress thread, since the 5-degree side is the load bearing side, this doesn't have a tendency to self-center. If you have a standard metric thread with 60-degree thread angle, that has a certain tendency of self-centering between the ID and OD thread, because it's just a row of taper fits behind each other with the thread pitch spaced apart with a 60-degree taper. That has a self-centering tendency. And that can pull if the runout between the drawbar and the pull stud on your tool holder are significantly off. That can pull it off center. That can cause problems. And I think Deckel chose this because this doesn't have the self-centering tendency. And to further strengthen this theory, we look into the book Foundations of Mechanical Accuracy by this Moore Special Tool Company, a company that knows a thing or two about precision. They had chosen a square thread for their chick bora tooling, because their theory was that a square thread doesn't have any self-centering tendency, meaning doesn't have a tendency to tilt the tool in the spindle taper one side or the other. It's a very small amount that would happen because it's all very solid, but it's all elastic and things will bend under side loads, and that way they overcome this problem. If it was really a problem, but they did, and that's why I think Deckel did the same. Long story short, I need a threading tool for cutting this thread. And it will look like this. I will just take a piece of 6mm carbide, 45 on one, 5-degree on the other side, about 10 degrees clearance on the leading edge, because it's a 2mm pitch, and 4 or 5 degrees on the trailing edge. 0-degree top break, just breaking the top corner a little bit with a diamond hone, and call it good. We're over at the D-bit grinder. I have a piece of 6mm carbide, well, Nen mill, and we'll start. This is set to 0 out here. We'll put this at 45 degrees, and we'll set it to our 10 degree of clearance down here. This is not a precision setting. It's just clearance. And I don't split it in half before I grind the angles this time, because I want to try something new. I want to grind the angles first and then split it in half, just for the sake of it. Putting a rag here. Don't do that with the rag. This is dangerous. If you do this on your own behalf, and don't blame me if something explodes. So now we're just going to grind the first face of the tool. That's the first clearance flat. Now I need to spin the tool 180 degrees. This needs to be set to 5 degrees, which is the load-bearing side of the thread. And down here, this joint, this is the clearance angle. We need to set that to -5 degrees. We're now grinding upside down. We're just setting it approximately to 5 degrees. And we need to move this over. So we're back into our work envelope of the grinder. And we're good to go. If you wonder why I put the rag here, it's easier to throw the rag away once it has carbide dust all over it than clean the grinder each time before I move any adjustment. You still have to be careful with moving stuff around and not getting carbide grit between the moving parts, but this helps a lot. This will be more of a plunge grinding operation. I will oscillate back and forth and very slowly infeed. There we go. That's looking very awkward right now. When you look at it like this, you can see the 45 on this side and the 5 degree on the other side. Now we just need to grind the top rake to finally form the tool. For that, we put the tool at 90 degrees and we put this back to 90. And this lower joint here also goes to 90 or 0, depending on the direction you're counting. Now we're just grinding a little bit of a step in here to create the top rake. You can see that's quite a good fit. Well, let's go to the lathe, set it up for threading, and see how this goes. Okay, off camera I prepared the blank. This is 4140. This section here will be threaded with the S20x2. I left a smaller diameter section here on the end. I need that when I flip the part around, so I have something to grab on in a chuck. I don't want to clamp on the newly finished thread. And the other side will get the 5/8. Also, you notice that there is a life center supporting it. These tools, buttress thread tool, will put in quite a bit of cutting force. So I'm taking it easy and using tailstock support here. I'm not a big fan of using a tailstock because it's constantly in the way, but it is what it is. Oh yeah, I'm running 60 RPM. Okay, let's do a scratch pass. Wow, the blue shows up great on camera. Okay, let's check the thread pitch. Always like to idiot check it because, well, I make plenty mistakes, and that looks like 2 millimeters. So time to thread this. This will take forever. I'm going to take fairly light cuts because this tool is not overly supportive to itself. Oh, hey, turns out this is quite a good fit. This is the collet nut from my D-bit grinder. Yeah, this. Well, I just wanted to try it, but that's already pretty darn close. Doesn't look too bad. Need some. If we clean it, if we, yeah, that's a nice. You can see the surface finish on the flanks of the thread. I'm pleased. Let's get the tail stuck out of the way. I'm going to leave the thread like this. The nut of the D-bit grinder fits very nicely, and I don't expect the drawbar of the milling machine to be different to this. Yeah, that feels about the same with a commercial high quality S20 by 2 pull stud. I'll run a piece of Cratex over it to remove the burrs on the top of the thread and call it good. Threading the second side, 5/8 11. I set the change gears and turn my Audi, so ready to go. Slow speed. Ooh. Ooh. Uh. Oh yeah. Okay, that's it. I'm leaving it like that. Need some deburring. I finished it. I ended up with a little bit over one and a half threads or so, because I have to deal with the limited thread depth in the hardened piece here. But it is what it is, and I think it will be fine since it just needs to hold a microscope in and not withstand hogging with a 32 millimeter roughing end mill. So when I put this on here, it seats against the face here, and at least by eye, it runs true. I had to loosen up everything a little bit. I get, let's see, 30 micron here. I think I get plenty more out here. I get 670 out here. 70 micron. It's probably fine. You have to really seat this with some authority, because the hardened thread in this holder here, they moved obviously a little bit when this was hardened. So everything in there is a little bit, well, it's not ideal. Let's say it that way. But still, I think it will work. Let's put it in a mill and check the run out. I have the thread adapter in some wooden jaws. I'm just going to, just like this. Leather gloves, obviously, to give me a little bit more grip. This will be totally me doing this the first time without trying it off camera first. Breaking loose the 40 taper reduces leaf for the collets. Cleaning the taper. Let's see if this thing fits. Make sure it's clean. It screws in all the way at least. Now we'll give it a medium grunk on the drawbar. Let's get a dial test indicator on the precision diameter here. Keep in mind that the spindle of the mill obviously has also run out. But let's see. Ooh, that's nice. Okay, a little bit of drawbar pull stud eccentricity obviously doesn't create a problem, because when you look at my dial test indicator here, it appears that it's broken, but it's not. And these Giraud are really sensitive. These are really good dial test indicators. This is a 2-micron reading indicator. This is not the... Oh, hot damn, this is really good. This is in the 2-micron range. This is not the ideal indicator stand for this, obviously. Yeah, this is like 2 microns. Could break out the electronic indicator, but it will be fine with this. Yeah, I'm very happy. This looks excellent. Uh-oh. Uh-oh. We are in trouble. The adapter, obviously, stayed in the spindle. Oh no. That's why I need to Loctite the adapter into the... Oh my. I hope I don't have to... There it is. I was already worried that I had to take the drawbar out of the spindle. That would be embarrassing. Loctite 648, some gloves, because Loctite is not exactly healthy. And yeah, I know that that these gloves, these are nitrile. They will only hold up to acetone extremely short amount of time. When I machined this, there was an extension on this end of the pulser. I just hacksawed that off with a hacksaw and cleaned up the end by face grinding it on the D-bit grinder. Everything is clean, and I will use a nice amount of Loctite 648, and hopefully this will permanently bond these two pieces together. Without ever coming apart again. I suppose I could put a chain wrench on here, but that feels wrong. Yeah, that's tight. Okay, there's the modified shank. I think it looks okay for modifying a pretty high-end tool. So I think it's absolutely the right call to modify a tool to make it usable. Otherwise, this would be trash, or a piece for a conversation piece on a coffee table, but that doesn't help anyone. I think this is way better used this way. That's the microscope mounted back on the shank, and now it's in the spindle of the mill. And as you can see, the internal lighting of the microscope also works. Since I don't have 110 volts available to me, I cut the cable and I'm running it off my lab power supply. It takes 3 volts and it pulls 1 amp. So let's have a look through the eyepiece. Okay, that's my setup to film through the viewfinder of the microscope. The phone works better than the DSLR for this. I don't have a good lens to film into the eyepiece. And we're looking down at a steel scale with at the 1mm graduation up here. So you set the focus by moving the Z-axis up and down. I haven't locked the focus of the camera, well, of the phone. So this gives a little bit of a, a funny effect, but at some point both the crosshairs or the hash marks and the object we're looking at are in focus like it is right now. And when I move the table in X now, you can see what's going on. And it's really nice. You can line up the crosshair, for example, with the side of one of the millimeter marks on the steel scale, zero out the DRO, and move to the edge of the next line, like this, and measure the actual distance, for example. So up here you can see that I measured a distance of 1.015 millimeters between the two lines. Or if you want to find the center between two features, you move to one spot, line it up, you zero out the DRO. You move to the other side that you want to center up, like here. Zero up the DRO, and you crank to 0. Well, you split the value in the DRO in half, and then you move to 0. Now we're right smack between those two lines, just by using the optics. And this is fairly precise. Doing blind tests, not looking at the DRO, I was able to repeat within, well, 2 to 5 micron. And I think in reality you can giving it some tolerance and leaving the machine tolerance itself out of the equation, I think you can hit repeatably plus minus 5 micron, giving you a total band of tolerance of 10 microns. We're over to Decal FP1, and off camera, I made the adapter for the Moore centering microscope. I did it off camera because it's basically cutting off the shank, and I will show some pictures how it's made. Starting out with the microscope after removing the adapter for the jig grinder. The 4-threaded holes are 1024 UNC. The way I wanted to interface with the HSK adapter didn't allow for the 1024 socket head cap screws. Their head was a bit too big, so I had to find a different solution. I decided to put metric solid threaded insert into the microscope to reduce the threads down to M3. Their smaller head would allow for clearance around the HSK holder. The microscope is carefully clamped down onto the faceplate of the milling machine, and I drilled out the original threads and tapped them M5 by 0.5, which is the outside thread for those NSAT threaded inserts. These threaded inserts are self-cutting. You can tap them directly into a drilled hole, but that requires a lot of torque, and I prefer to thread the holes in a separate step with a matching tab and Loctite the inserts in. I sketched out how I wanted to mount the microscope. I cut down a HSK 32 weld-on tool holder to be as short as reasonable possible. I would make a flange that clamps onto the tool holder with 4 set screws in the V-groove of the holder, and this gives me the mounting flange for the microscope. Drilling and tapping the radial holes for the set screws in the flange, the finished flange ring, the set screws, and the cut down HSK tool holder. Assembled with Loctite 648 between the flange and the HSK tool holder. The set screws are also Loctited in and tightened into the V-groove of the tool holder. This is very much a permanent assembly. The modified HSK holder went into the horizontal spindle of the mill using the HSK 32 to 40 taper adapter, and I faced it in situation with a lathe tool for optimal axial runout. The completed assembly with the microscope and tool holder joined. You can see the 4 M3 screws holding everything together. Note that I still had to turn down the heads of the screws a bit and machine very close fitting counterbores into the flange ring to make everything fit. By the way, the radial runout between the microscope and the tool holder is not super critical. On both this and the Nikon microscope, you can adjust the crosshair to be true to the center of rotation. But the idea is this goes into this adapter, takes about 3 turns, it's locked. I can look in here, do my alignment using these 3 axes of the milling machine. Well, the y-axis to set my focus and X and C in case of the horizontal spindle to align my work. And when it's time to do the cutting, it's as quick as doing this, taking the microscope out and putting the cutter back in and ready to go. The Moore microscope does not have internal lighting like the Nikon scope. Of course, I can use the Nikon scope directly in the 40 taper horizontal spindle too, but I have one part family that I do with the HSK adapter because I have several tool changers within one setup, and this is just so fast. This drops in, and it's really, really, really precise. And do my alignment, and rotate the eyepiece how I need it. There are 4 set screws radially, and these move the crosshair on the inside around. I think rifle sights are adjusted very similarly. At least the one I took apart years and years ago. But yeah, this is the centering microscope. It works really well, and I hope that this will make my life easier. But since this is HSK 32, it also fits my CNC milling machine, which, well, it takes up quite a bit of C height. But this is the focal length from here to here. This is the focus distance. And, well, it's still usable. Can go in here. I can do measurements or picking up 0 and do absolutely not turn on the spindle while it's in in the tool holder. But yeah, that's the HSK 32 Moore centering microscope. Here are the 2 finished centering microscopes. I need to get a 3-volt 1 amp power supply for the Nikon scope, because this power brick here, while the voltage can be switched around, it can be changed between 100 and 120 volts. That's not super helpful. But I will try to find something that has 230 to 3 volt. Maybe I will just use a USB-C charger with a 3-volt power regulator or voltage regulator behind it. I'll see. That's not exactly a mission-critical problem. For the time being, I can just hook it up to my lab power supply. But yeah, now I can put it to good use. I think this modification is very clean. This modification here is a little bit more ad hoc, but HSK holders are always a little bit annoying to adapt because they have all this infrastructure around them, all these slots and cutouts for the automatic tool changer. But in this case, I could use the V-groove for the tool changing gripper to my advantage. still fits in the original box, and it appears that this plate was original because there is a spot up here all ready to use. That's the Nikon centering microscope. But building my own centering microscope, this idea never really died in my head. And also playing around with optical components led to this thing. This is just I think it's a observing scope. And it has a 4 power lens and a 10 power eyepiece here, but I moved them together very close, so the overall magnification is not 40 times, as far as I understand. But the working distance is quite significant, and I use this when I do micro drilling or micro sawing on the milling machine here to observe the cutting conditions, and it's working very well for this. I will play around with this a little bit more, and I will do a separate video on it at some point in time, probably, maybe. Don't nail me down on this, but I will try to not forget about it. But yeah, I'm still playing around, and due to the fact that this has a 45-degree prism in here, you could put a shank here with run-out adjustment and make this into a centering microscope, into a DIY centering microscope. So that would be quite cool if there was a DIY solution. People have built DIY centering microscopes. There's also people who built solutions with cameras, digital camera microscopes or similar things. Very famously, of course, Mr. Dan Gelba, who has the wireless camera on his jig borer, spindle mounted, which is quite cool. But I kind of like a simple optical solution that doesn't require electronics, if possible. Well, it has electronics for the light, of course, but not anywhere in the optics path. So, long story short, my immediate centering microscope needs are solved, but this idea is not dead. Thank you all for watching. I hope you learned something. I hope you. I'm always trying to show you some interesting setups, and also that modifying tools is absolutely okay. If a certain tool is absolutely of no value for you or when you want to sell it, well, it's not modified. Make it do a good job of the modification, of course. Don't do a hack job. Don't just, well, use a wire feed welder and weld on a different shank, but do a proper job, and well, it's absolutely okay. And also, you don't need my permission to do anything, so be your own judge. So thank you all for watching. Thanks for your support, and I'll be back.